Hi, my name is Dave Thibodeau. I'm a principal R&D engineer at Knowles Precision Devices in Casanova, New York. I've been with Knowles almost 4 years. I have over 42 years of design and development experience in RF and microwave components and systems. Today, I'd like to talk about compact quadrature hybrid couplers. What are they? Quadrature hybrid couplers are basic building blocks for many RF and microwave systems. They provide equal power split to two outputs. They also have a 90-degree phase difference between those outputs. The diagram at the right have shown a depiction of this. You put power in the input port, and the port opposite is a coupled output port, which is 3 dB down and a relative 0 degrees phase. Diagonally from the input is the direct output, or DC coupled output. It's also 3 dB down, but it's minus 90 degrees phase relative to the 0 degree phase on the coupled output. The isolated output is typically greater than 20 dB down and is connected to a 50 ohm termination. The 90 degree phase difference between the direct output and the coupled output is inherent because of the quarter wave coupling section. It is also notable that these devices are symmetrical devices, so any one of the 4 ports could be an input port with a relative positioning for all the other ports. Why are they important? They provide improved input match for unbalanced loads. The energy splits evenly between the outputs. Some energy is reflected back due to mismatch. There's a 90 degree phase difference between those two outputs, so that the reflected energy at point A is 180 degrees out of phase and cancels at the input port. At point B, the energy is in phase and sums at the isolated port, which is terminated. Provides good input match for unbalanced loads. How are they used? Other basic building blocks for many RF and microwave systems. In addition to being used as a power splitter combiner, such as in feed networks and Butler matrices, they can be combined with some type of identical function blocks at the outputs as shown in the diagram, and the resultant energy will come out the combined function output. For example, if you use detectors for those function blocks and provide a LO drive network to those detectors, you wind up with the IF at the combined output port. It becomes a unbalanced mixer or modulator. If you use pin diodes for those function blocks, provide a biasing network to switch those diodes on and off, the combined function output is a switch. The energy coming in the input is switched on and off to the combined function output, depending on the state of the pin diode bias network. You can also use some type of variable resistance, again, typically a diode with a bias network. And as you vary the level in the diodes, at the combined function output varies appropriately. If you use a variable reactance, such as a varactor diode on the function blocks, and provide a bias network, same deal. The input level comes off the combined output with variable phase depending on the state of the reactance of the diodes. How are they used? Well, you can also use them with 2 devices with identical function blocks connected between them, as shown at the diagram on the right. You provide an input signal at the input port, and then depending upon the function blocks you use, you get a combined output, which is the input minus the insertion loss of the couplers, plus whatever the effect is of the function blocks you've chosen. So if you put amplifiers for those function blocks, the power will divide, go through the amplifier stages, provide gain, then recombine, and you wind up with a combined output, which is going to be 3 dB higher than the gain of the individual amplifiers. Similarly, if you put in detector diodes in the function blocks and provide an LO drive signal, perhaps the isolated output port, The combined response at the output would be the IF product. Again, using variable resistances in the function blocks, you can wind up with a variable attenuator function. Similarly, variable reactive elements such as varactor diodes provided a variable phase shifter. And if you used, again, pin diodes or some other type of switching device, the input can be switched on and off to the combined output. In the past, designers have used several methods. Surface mount devices are available to 12 gigahertz. They're typically narrow band and low power. There's also connectorized packages, SMA, Type N, etc. They're very large, heavy, expensive. They provide good performance and can handle high power levels. Lane couplers are typically narrow band, they're wire bond, and they're lossy. They can also be integrated into the motherboard, but because of typical printed wire board tolerances, the RF performance tolerances are very loose, or it would be very expensive to control the printed wire board to get the type performance of the RF performance you desire. You can also use Wilkinson dividers. They're available in surface mount or connectorized. They're low loss, low power, provide 0-degree offset. They have similar applications to dual hybrid couplers, but they're not going to be balanced. Knowles is offering some new options. We're providing quadrature hybrid couplers 4 to 8 gigahertz, 6 to 12 gigahertz, 10 to 20 gigahertz, and 6 to 18 gigahertz bands, and other bands can be available upon request. We're offering them in surface mount and wire bond versions, and they have small size. They provide low loss, good amplitude balance of better than plus or minus 0.7 dB port to port, good phase balance, better than plus or minus to the 90-degree offset. Return loss is better than 15 dB. Isolation better than 20 dB. And power handling can be greater than 50 watts CW with a proper thermal design. They'll operate from minus 55 to plus 125 degrees C, and they're low cost. Summary: our new quadrature hybrid couplers offer new choices to the RF microwave circuit and system designer. We have surface mount wire bond versions, wide bandwidths and ranges from 4 to 20 gigahertz, low loss, low cost, small size, high power. A nice addition to your design toolbox. Thank you.